Okay, so starting with chapter P, the prerequisites chapter, which we'll go through pretty quickly just to make sure that we're all on the same page with the things that you're supposed to know going forward. So P1 and P2. P1 is about mathematical modeling. Okay, so mathematical modeling has to do with using math to solve problems in the real world. So this is a picture of Haiti after the earthquake in 2010. So what questions about that earthquake might we be able to use math to answer? Yep. Yes, so we could look at a time, we could be able to figure out a timeline. Yeah, good. Yep. Magnitude, which is how we mathematically measure the strength of an earthquake. Yep. Sure. You could have something about the number of aftershocks, the strength of the aftershocks. Maybe we could have an equation that would predict strength and frequency of aftershocks.
The amount of reported injuries.
Yeah, number of injuries, med supplies needed. Great. So there are tons of things we can use math for in the real world, and a lot of them deal with creating a relationship between two variables so that we can make predictions. So a model is a mathematical representation, such as a formula, but also a graph or a table of values of a real world situation. If you can describe the relationship between two or more quantities, then you can write an equation that relates them. So this is an important step in problem solving, being able to convert a description in words into an equation. So here's a model that we should all be familiar with. The model of distance of an object has traveled is equal to the rate it's traveling times the time it's been traveling. D equals RT. So D represents the number of miles the object has traveled, R is the rate in miles per hour, and T is the time in hours. And we have this nice mathematical model that relates those three variables. So I want you to, in your groups, come up with at least a couple of other models that you're familiar with. Formulas that relate variables are mathematical models. And make sure you talk about what the variables represent. Okay, anybody willing to share one of their models? Slope? So what in real life, where in real life do we measure slope? Mm-hmm. Sure, okay, good. So slope we calculate as rise over run. And it has tons of real life applications, the grade of a road, the pitch of a roof, the steepness of stairs, yeah. The cost of a textbook, yeah. The rate of change, how it increases every year, yeah. What other models? Yep. Momentum, what is that? Momentum, mass times velocity. Great, so my formula, do we have a symbol for momentum? P. P is m times v. Great. I defined the variables up above. Good, so there are tons and tons and tons of mathematical models of different ways that we have variables that are related in real life, like the gas mileage of your car. right? You divide distance traveled by number of gallons of gas used, and you get miles per gallon. So there's just a ton of them. And here is another one. So it turns out that the portion of an iceberg that's below the water is much larger than the portion that you can see above the surface. Hence the adage, it's just the tip of the iceberg. So the total volume of an iceberg is modeled by this equation. V is for total volume is equal to 9.5 times S, and S is the volume above the surface that you can see. So total volume is 9.5 times the volume you can see. So what's the total volume of an iceberg if the volume you can see is 4 cubic kilometers? So before anybody answers, which variable am I going to replace with that 4, V or S? So we have a consensus? S? Yeah. Because the volume showing is 4 cubic kilometers, and S represents the volume showing. V is the total volume of the whole thing. Yep. So my total volume V is going to be 9.5 times 4, which is 38 cubic kilometers. Now I want to find the volume that you can see if I know that the total volume is 19. So which variable am I going to replace with the 19? V. Good. So I'm going to have 19 equals 9.5 S. And how do I solve for S? Divide by 9.5. So we get S is 2. So this is just the tip of the iceberg for mathematical modeling. So a very small, brief intro. We're going to be doing this all semester, applying the different kinds of models that we learn about to real life things. Okay, so we're going to move on to section P2, the real number line and order. And I just want to point out these little numbers, P.3-1, they should really be P.2s because we're in P2 and I messed it up, sorry. But yeah, it's not that big a deal. So this year we're going to spend some time solving equations and inequalities. That's part of what we'll do. And we're going to need a precise and concise way to talk about what the solutions are. Okay. So we're going to use something called a tool called sets in order to do that. And a set is just a collection of objects. So we could have the set of students in this classroom, the set of blue cars in the lot, or the set of Oscar winners for Best Actress. It's just a collection of things. So you can write a set by listing it between curly brackets, curly braces. So if I wanted A to represent the set of the Three Stooges, then A would equal, curly brackets, Larry, Moe, and Curly. Okay. Or if I want B to represent the set of the Seven Dwarves, then B would be, what would be in set B? Grumpy. Oh. Bashful. Sleepy, is that one? Yeah. 1, 2, 3, 4, 5, 6. There's one more. Happy, of course. So you just list them out in curly brackets, commas between them, and you have a set. So the individual objects in a set are called the elements of the set. So let's name one element from set B that does not end in Y. Doc. Or there's one other, what is it? Bashful. Okay, so the sets we're going to encounter in this class are often going to be sets of numbers. We're not going to be talking about sets of the 7 dwarves, right? I know. So we have some ways to write sets of numbers, because sometimes our set of numbers, there'll be so many numbers in the set that it would be crazy to just write them all out in between curly braces. So we have some other ways to do it that are going to help us. The first one is called set builder notation. It's a descriptive way to write a set, and generally speaking, it looks like this. Curly bracket, X, vertical line, X meets some condition. And the way you read this is you would say, okay, the set of all X's, and this vertical line you would read as such that. So the set of all X's such that X meets some condition. So for example, I could write the set of all X's such that X is less than 0. Okay. So that's how you would read it, the set of all X such that X is less than 0, which you would interpret in your brain as the set of negative numbers. Okay. So to talk about solutions to inequalities, we often use set builder notation. So I could say the set of all X such that X is a solution to this inequality. Or I could be shorter and say the set of all X such that 3x minus 6 is greater than 15. So what numbers X belong in that set? Okay. X is greater than 7 are the numbers in that set. Yep. So we can solve the inequality, and you get X has to be greater than 7. So this set is equal to the set of all X such that X is greater than 7. So this is a nice handy dandy little way to write out the solutions for inequalities. And we have another handy dandy little thing for when all of my X values lie in some interval, has some lower bound and an upper bound, and it's all the X's in between. So for example, if I want to graph this thing, I have the set of all X's such that -4 is smaller than X, but X is smaller than -1. So my written description is all numbers between -4 and 1. So it's sandwiched between -4 and 1. Does it include the 4? No, because it's strictly less than. Does it include the 1? Yes, because it's less than or equal to. Okay, between -4 and 1, including the 1, but not the -4. So to graph that, I want to shade all the numbers on the number line that are included in the set. So the way I show that -4, I go all the way up to -4 but not include it, is with an open circle. So I put an open circle on the -4. I include the 1, so I'm going to put a closed circle there, and then shade all the numbers in between. Those are all the numbers in my set. So I have a shorthand way of expressing this set called interval notation. Okay, so instead of writing this slightly cumbersome the set of all X such that notation, I can use something called interval notation, where I would just write -4, 1, meaning all the numbers between -4 and 1. A round bracket means don't include the endpoint, and a square bracket means include the endpoint. Okay, so round bracket -4, 1, square bracket means this. You say the set is open at -4 and closed at 1. And square brackets around 2, 3 means all the numbers between 2 and 3, including both the 2 and the 3. And this one, -1, 5, this is an example of an open interval, open on both ends. It means all the numbers between -1 and 5, not including either endpoint. Something to be a little bit careful of is that this looks a whole lot like what? Something else that you've seen in another math class. A point, yeah, this looks like an x comma y point. So we're sort of repurposing a notation that you've used for something totally different. So you have to gauge from the context of what you're working on whether or not this means the point -1, 5, left 1, up 5, or the interval of x values from -1 to 5. It should be clear from whatever problem you're working on what it means. So this one we call neither closed or open, or some people say it's half closed or half open. Okay, so I want to graph these number lines and write the set in interval notation. I want you to try it in your groups. All right, so that's good. It seems like people are pretty comfortable so far. So moving on to the next one. Take a couple of minutes to, this time I'm giving you the number line. I want you to write the interval notation and write the set builder notation. Take a minute or two to do that in your groups. So let's see. The interval notation is the easier one, I think. It's a little quicker. So we'll do that one first. So for this one, I'm going from -1 to 2, all the numbers between -1 and 2. I'm including the -1 and not the 2, so I go square bracket, round bracket. And then this one goes from 1.5 to 4. So I put 1.5 comma 4, and I'm including both endpoints, so they both get square brackets. And then this third one's a little tricky. So this one's going from 3 to what? Yeah, it just keeps getting bigger and bigger and bigger. So it's going from 3 to infinity. So that 8 on its side is the symbol for infinity. Takes a little practice to be able to draw it well. Now, I'm not including the 3 because there's an open circle there. What do you think about infinity? Do we include it or not? Yeah, it's always open because infinity is not actually a number. Like if I told you to count to infinity, you couldn't do it, right? You can't actually get there. So infinity is not something that you can include in a set. Infinity is an idea of getting bigger and bigger and bigger. You can't include it because it's not a number, so you always put a open bracket. All right, so let's translate to set builder notation. So I want all the x's between -1 and 2 here. So I'm going to put the set of all x such that, and then I want to sandwich my x between -1 and 2. So I like to do that. I set the sandwich up, and then I'm going to sandwich it between -1 and 2. And then I decide where to put the or equal to's, right? I include the -1, but not the 2, so I'm going to put an or equal to with the -1. Nope, because I want to have a closed dot on the -1 and not on the 2. If I put an or equal sign here, then I would have had to have put a closed dot on my 2. Yep. Now this one, I'm sandwiching the x's between 1.5 and 4. So I have the set of all x such that, and then I'm going to sandwich my x between 1.5 and 4. And then I decide whether or not I need or equal to's. And in this case, I need them on both because I have closed dots on both numbers in my number line. So I put or equal to. And then the last one, set of all x such that, how do I express what x values are shaded on that number line? What about -3? There you go.
Do you have, like, the infinity there?
You don't need the infinity. If you just say all the numbers so that x is bigger than -3 or -3 is less than x, that implies to infinity. So this is the one exception where you would be allowed to not write it left to right, small to big. So you could write the set of all x such that x is bigger than -3. That's the one exception. When you just are doing an interval from one number to infinity, you can just say x is bigger than that number. Okay, so now that you've seen that it's okay to write infinity when you're using interval notation, do these two. Graph the set on a number line and then write them in interval notation. All right, so the set of all x such that x is bigger than 5. So I'm just going to randomly put 5 on my number line right here. So I'm not including the 5 because it's just bigger than. So I put an open dot. And the number's bigger than 5. Is that to the left or the right of 5? The right. So I shade all the numbers to the right. Okay, so in interval notation, how would I express that? You got it. Good. And then I want x's less than or equal to 2. So here's my 2. It's an or equal to, so I get to include the 2. And then less than, left or right of 2? Left. Okay, so, when I go really far this way, I call that infinity. What should we call it if I go really far to the left? Negative infinity. So I'm going to go negative infinity to 2. Never include an infinity because you can't get there. And I am including the 2 because I put a closed dot on it. Okay, so last thing, we are going to use set builder notation on a couple of real life situations and interval notation. So the set of temperatures for which water is a liquid. What is that? I don't care. Sure. So 32 is the freezing point. So let's call this the set of all T. We'll use T for temperature. Set of all T such that, now 32 is the low. Less than T, less than, what's the boiling temperature of water? 212. Now I think it's the case that 32 is the freezing point, so at 32 it becomes ice. So I'm not going to include the 32. Same thing with the 212. That's the point where it becomes steam, so I'm not going to include the 212. And so if I were to write this in interval notation, it would be 32, comma, 212, round brackets. And I should put a little note here that T is in degrees Fahrenheit. Now, if it was Celsius, I would have had what? 0 to 100. Good. Okay, so what if I wanted to express the set of heights that allow you to ride a roller coaster if you have to be at least 60 inches tall? Let's Sure. So we'll say the set of all x such that 60 is less than or equal to x. Good. Yeah. X has to be bigger than 60. So, or you could write it that way too. This one feels a little bit more intuitive, saying number if you're taller than 60, right? But this one says the exact same thing. Just remember that the alligator eats the bigger number. So this says the same thing as this. So in interval notation, how would I do that? $60 to infinity. Never include infinity. Do I include the 60? Yeah. Right. So if you're 60 inches tall, you get to ride. That's a good point. In reality, there is probably some upper limit on height. I don't know what it is though. So we'll just say there's probably some upper limit, but we don't know what it is. But the sign says you have to be at least 60 inches tall to ride. So if we're just translating that sign, it would be 60 to infinity. All right, the set of ages that are eligible to vote. If 18 is bigger than your age, can you vote? So you just said, let me write it down. So you said the set of all x such that 18 is bigger than or equal to. Yeah, you had it the wrong way because this would say that under 18 can vote. Right? So we just switch this so that the age that you are has to be bigger than 18. Right. Yep. And you are an American citizen and not a felon, right? Yep. So we would go 18 to infinity. And again, there's probably some upper limit to the age that you can vote just based on how old a person can live, right? You can't, right? But if there was someone, you know, it doesn't matter how old you are, okay? As old as you can get, you can vote. So we'll leave it as infinity. Okay, so for homework, I want you to, again, I created some of the stuff for today a little bit too far in advance. I made a couple little changes because I realized I wrote down homework as though you were doing homework out of a book, and you're not. So just cross out what I wrote down for the book work. Your homework is this: A, B, C, D, and E from a packet that I am going to give you. From this packet. That's just some prerequisite stuff. It shouldn't take you that long. And then you're going to do read P1 and P2, which is what we talked about in class today. And you're going to do the assignment in WebAssign titled Class 1, which is due Monday.